So how does the histamine binds to the H2 receptor? So if we understand this binding mechanism, then we can easily understand that how the antagonist works in the receptor, H2 receptor. So at first, so this is histamine molecule, and this whole region is the receptor. Like at first we are seeing at in context of the H1 receptor, but we'll be seeing H2 receptors. But first, like what is the difference between H1 and H2 receptor, and differences in like interaction in the difference interaction mainly determines the differences in the molecule that we need to develop in H2 or in H1 receptor. So this is the pocket of the receptor, and there are different domains like binding domains or binding regions. Like this whole region is the receptor region, and this is one domain, and this is one domain. So one domain mainly interacts, or like this histamine, this nitrogen interacts with this portion of the receptor H1, and this side chain terminal nitrogen or terminal amino group, alpha amino group, mainly interacts with this receptor in case of H1 receptors. So like in case of H2 receptors, the slightly difference that is, like you can see, like the histamine molecule is like three interactions are active here, like one extra, like this in H1 this nitrogen was, there is no bonding between hydrogen bonding between the receptor and nitrogen molecule of the histamine. But in case of H2 receptor, you can see one extra bonding is here. So this mainly determines like how can we develop the molecule for H2 receptors. So this alpha amino group, this one, is involved in the binding interaction with both types of receptors. So both types of receptor, the ionic bonding or the hydrogen bonding, while the other nitrogen atoms, so within the heteroaromatic ring, so this nitrogen atom mainly interacts via hydrogen bond with the receptor. Also this one is interacting with hydrogen bond. So now we'll be seeing how does an agonist work here in the H2 receptor, and how it blocks the function of the H2 receptor. So likewise, this is histamine, and it is unbound state. When the histamine will bound in the receptor, then the receptor will activate. So now it is in active state. So when histamine comes and like attach with this two interaction sites of the receptor, then the receptor is activated and functional. So this, when the histamine comes and attached to the receptor, and the receptor is turned on, and this turned on mainly induces a change in the receptor shape. As a result of the change, the intracellular cascade pathways mainly activates. Subsequently, like signal transducer, different sorts of pathways gets activated because of this histamine binding to the receptor, and the receptor changes shapes. So as a result, the downstream result is like the release of the proton from the proton pump. So this is the state of the receptor when it is activated by the histamine. So what happens in case of an antagonist? Like this is your histamine plus one extra molecule. You can see this blue one is extra functionality. So like you can see there are a lot of binding sites or binding domains in the receptor. So the extra functionality will bind to another extra domain of the receptor. Like you can see these two, in this example, these two domains are bound, but here these two will be bound as well as this third one, because of the extra functional, because of the introduction of the extra functional groups in the molecule. So this is the antagonist. So what happens when it binds? Like whenever the extra site binds, like the whole shape of the receptor has to change, right? What we saw in the earlier example. But whenever this extra site is involved in the binding interaction, the whole receptor cannot change its shape. So as a result, if it cannot change its shape, then the receptor will be inactivate. This inactivated state is like blocking the receptor. H2 blocker is blocking this receptor or inhibiting the receptors. So the take-home message is like the agonist mainly binds and activates the receptor, and the antagonist works in the similar way, but the antagonist will have one or more functional group extra to that agonist, so that those extra regions will interact with extra binding regions of the receptor. So as a result, the receptor will have some sort of abnormal changes, or the receptor might not change at all, so depending on the receptor type. So this is how the H2 antagonists mainly work in the H2 receptors. So now we will be seeing the SAR of the H2 antagonist. So this is histamine, like we know this, and histamine antagonist quite similar, like this pyrimidine ring is here, and this side chain is present, and at last there is nitrogen. So this is the like core skeletal of the very simplistic structure of the H2 antagonist. So as I told, the H2 antagonists are histamine congeners with a bulky side chain in place of ethylamine moiety. So this ethylamine moiety, this moiety is replaced by a bulky side chain in the H2 blockers. So we saw that the extra side chain will interact with extra regions of the receptor. Next, so in this structure of H2 antagonist, this imidazole ring is not required for the activity, but like we will be seeing the ranitidine or nizatidine, those drugs mainly have different heterocyclic rings such as furan rings or thiazole rings. So by changing like this pyrimidine ring is not necessary, not mandatory, but changing the ring to another heterocyclic rings will increase the potency of the H2 blocker. So the next requirement of antagonistic activity is like the nitrogen, this terminal nitrogen, and like this ring, and between this ring structure and the terminal nitrogen, this distance should be separated by 4 carbon atoms for optimum activity, 4 to 5 carbon atoms. And sometimes in between these two there is a thioether like sulfur or thioether bond between these 4 carbons in different H2 blockers. So the terminal nitrogen, this nitrogen should be polar, like here we see in the histamine, this is charged, so this is polar, and this nitrogen should be non-basic substituents for maximal antagonistic activity. So in general, this antagonistic activity varies inversely with the hydrophilic character of the nitrogen. So if we increase or if we change the nitrogen here in a way that mainly increase the hydrophilicity or water loving nature of this nitrogen, then this will drop the whole activity, antagonistic activity of the molecule. But in case of ranitidine and nizatidine, this is not followed in these two drugs, but in general this is what follows. Like this nitrogen, if we make it more water loving, then this whole antagonistic activity will decrease. So now the SAR of cimetidine. So cimetidine is the first successful H2 blockers in the market. So this is the earlier slide. It is more like it is more accurate of the structure of the antagonist, H2 antagonist. Like we have seen, like this ring and this nitrogen should be separated by 4 carbon atoms, and in the carbon atom there should be some molecule like thioether or sulfur, right? So this structure is more accurate. Like this structure of H2 antagonist is more accurate. Like this, in the earlier we seen that pyrimidine ring, but here it is aryl or heteroaryl ring. So the ring should not necessarily be the pyrimidine. So it could change depending on the different H2 blockers. So cimetidine is the structure of cimetidine. So cimetidine retains this histamine structure, the pyrimidine of the histamine ring. So a pyrimidine or imidazole ring, sorry, this is imidazole ring. So this imidazole ring is maintained in the cimetidine. So the next, so the introduction of the basic moiety guanidine. So this is the structure, is the guanidine structure. So in cimetidine, this additional structure, guanidine structure, additional attached to this nitrogen. So this basic moiety guanidine at the end of the side chain improves the activity. So this is in cimetidine, this is the guanidine is present. So replacement of imidazole ring. So earlier we talked about this imidazole ring is not necessary for the antagonistic H2, for the function of the H2 blocker. So replacement of the imidazole ring in compounds such as ranitidine, this ring is replaced by furan, or in the famotidine or nizatidine, this ring is replaced by thiazole ring. So those compounds are more potent or active than the cimetidine. So substitution at C4 carbon 4 site helps the selectivity of the compound or drug. So this C4, like this is 1, carbon 2, carbon 3, carbon 4. So this is substitution in this position. Like here, like this position can be substituted by different molecules. So different molecule can be replaced here, and this will cause more selectivity of the compound. So sulfur atom here increases the potency than nitrogen or oxygen atoms. So the last one is replacement of this N-cyanoamino group. So this one, this amino cyano group or cyanoamino group, if we replace it by nitromethylene, that will increase the potency. Like this one is nitromethylene. So in ranitidine, I guess this cyano group, amino cyano group, is replaced by this CHNO2.